My name is Amanda McCauley, and this is my Lab 5 video. The purpose of this lab was to observe and model the interaction between a falling magnet and a tube of aluminum. And the main physics concepts were Faraday's law, induced current, Newton's second law, Biot-Savart law, and magnetic flux. More specifically, Faraday's law says that changing magnetic flux induces an EMF. And magnetic flux is shown generally and analytically here, but it's just the magnetic field times the area. And for a magnet, this is the formula that's used to calculate the magnetic field, also called the Biot-Savart law for magnetic dipoles. Here's the setup for my lab, including the dimensions of my aluminum foil tube. And the concepts behind the physical experiment is that the falling magnet induces a current in the aluminum foil, which creates a magnetic field, therefore generates a magnetic force on the magnet that opposes the force due to gravity, causing it to fall slower in the tube than it would without the tube. So I did 5 trials of measuring the time it took the magnet to fall, and my average time was 1.29 seconds. For coding, I used the dimensions shown on the previous slide and the function to calculate the magnetic field from Lab 5. I'm using the Biot-Savart law for a magnet. And then I calculated the magnetic flux using this function, and this is just the analytical approach because it iteratively is counting the magnetic flux through each ring, and then the EMF is the negative change in magnetic flux with respect to time. So, and the current is just the EMF divided by the resistance. That's how I calculated the current. And then here is how we calculated the force on the ring, therefore the force on the magnet, since they're opposite. And there's how the R vector is shown on the top right. But the force on the loop is the current times 2 pi the radius times the magnetic field using the Biot-Savart law times sine theta. But sine theta can be simplified using the equation shown on the right, using the magnetic, the mu of the dipole moment of the magnet and the direction of the magnetic field. And then the overall net force is the force due to gravity plus the magnetic force. And then through each step, after iteratively going through each ring, updating the velocity and position using Newton's second law. So here is my velocity versus time graph, and while the magnet's in the tube, F net is equal to 0, as shown by the constant velocity over time. And in the experiment, I got 1.29 seconds, and the model had 1.561 seconds. But I think that this is due to potential error in my mu, or magnetic dipole moment, because in Lab 3, there's a lot of variety and a lot of different variables involved in how accurate your mu was. So I would probably do this again if I wanted these numbers to be closer. But in the model, you can see that there's a red section and blue section, and those are different direction currents. And I've shown below kind of the thought process behind each. So the blue is when the induced current is clockwise, using Lenz's law and the right-hand rule when calculating the negative change in magnetic field and flux. But here's just visualizations of that process. In conclusion, if the resistivity of the conductor is reduced as close as possible to 0, how would this change the dynamics? So if it was reduced, the magnet would fall at a slower velocity in the tube and take longer to travel the length of the tube. You can double check this using the glow script model. And if holes or slits or slots were cut in the tube, how would this affect the ring's current? So if the holes were cut in the tube, we cannot model the system as rings in a series because the rings of aluminum would be incomplete for some sections, so the current wouldn't flow through those areas.